look at 2014 50 through 60, and I just kind of decided that it wasn't worth making a video because I couldn't talk about that much orgo stuff or anything. So today we're going to 2015 1 through 10, and first up we have just equation balancing. Pretty much we have the combustion of benzene. So 6CO2 12, that's bad balancing. I don't know why there's a 6 there. Okay, so we have to balance the H's. So we have 12, 15. And we need to react to 1 mole here. So 15 halves equals 7.5. So that's how we get B. Oh, what did I just do there? Yeah, so number 2, 10-gram sample of a soluble barium salt is treated with an excess of sodium sulfate. Okay, so this is just stoichiometry. So we want to find the moles of precipitate that we got. 11.21 divided by 233.4. Oh my gosh, I can't type. We got 0.048. I mean, this would probably be more correct in terms of sig figs. So that's how many moles of barium sulfate we have, which means that's also how many moles of barium we have. So if we multiply by the molar mass of barium, that's like 129, I think, but I'm not completely sure. 137.3. Yeah, I was wrong. Okay, so if we multiply, then we get that in the original thing, we had 6.594 grams of barium, and if we do 10 minus that, then we had 3.40, I'm just going to say 6 grams of whatever the other thing is, and it has to be twice the mole value of barium, because we can see that all our anions here are -1 charge, so they have the 2 coefficient. So we have 0.04803 moles times 2, and then we do 3.406 grams divided by the mole value we got, and then we find that the molar mass of the anion here is 35.45 grams per mole, and that gets us chlorine. So number 3, what is the concentration of nitrate in that volume of a solution with that much stuff? So here, kind of the same thing as last problem, pretty much. So we're just doing 32 divided by 148.3, and then that gets us 0.216 moles of MgNO32. We have to multiply this by 2 in order to get the moles of nitrate ion in the solution. So 0.432 moles, and then we need to divide this by 0.425 liters to get the molarity. That's 1.015 or 1.02 molar. Okay. Formula for terbium phosphates is that thing. Okay, so we know phosphate has a 3- charge. That means this terbium ion is going to have a 3+ charge to balance it out. So we're looking for an instance where its oxidation state is 3. Here it would be 1. Here it would be 2. Here it would be 4. So it has to be C. 25 milliliter sample of silver nitrate is reacted with that much calcium chloride, which is true. Okay, so if we do 0.025 liters times 0.15 molar, we get this many moles of silver nitrate. And then if we do 3.58 divided by 111, we get this many moles of CaCl2. So obviously silver nitrate is limiting here. There's like 10 times less of it, and they're only reacting in a 2-to-1 ratio. And what precipitates? You can just eliminate A because nitrate stuff doesn't precipitate, so you would choose B. 6. Which aqueous solution exhibits the largest freezing point depression? So your change in freezing point is going to be equal to the Van Hoff factor times the freezing constant times your molality. I think it's more proper to write molality as lowercase b instead of lowercase m, but I'm just used to writing it as lowercase m. So here, you want this quantity to be the largest. And Kf, it's water, so you can stop looking at that because you're dissolving all of these things in water. Same solvent, so it's not going to have an effect. Here, what's changing are your I values and your molality, so you're looking for the largest product of them. So here your I value is 2, because you have KBr, a strong electrolyte, goes into 2 ions. Here it's 3, here it's 1-ish, here it's 5. 5 times 0.25 is 1.25. 0.75 times 1 is 0.75, that's less than 1.25. 1 times 2 is 2, 0.5 times 3 is 1.5. 2 obviously is the largest quantity among those 4, so that's why you choose it. Which is not appreciably more soluble in acid than in pure water. Okay, so here you're looking at what the anion is. If it's a basic anion, it's going to react with the acid, and you're going to make the compound more soluble in that particular condition. Here, basic, basic, basic. Not super basic, still basic, but HSO4- is a relatively strong acid. I think its Ka is on the order of 10 to the negative second, so it's a pretty strong acid. That means the conjugate base is going to be rather weak, so C would be our correct answer. 8, which reacts most vigorously with water? So when I first saw these questions, I didn't really know how to do them, but basically, you know, your answer is going to be from the alkali metals because they're just the most reactive metals. So get rid of these alkaline earth metals. You're looking at Na and K. The reason I reason it out to say K rather than Na is that K is 1 period below Na in group 1, and that means it has another level of s orbital to it, and that its valence electron is further from the central nucleus than Na's valence electron would be. So that means it's easier to pluck away, it's easier to react. So if it's easier to react, there's going to be a more vigorous reaction. So that's why I choose K. 9, all of these form a colored aqueous solution except, okay, so in the context of the USNCO, color means incomplete, not totally filled D subshell. Not totally filled, not totally filled, not totally filled, totally filled. 10, okay, this one's like common sense. You can't measure anything in a volumetric pipette except the volume that it was made to measure. So if this said 50, B would be right, but it's not 50, and if it's not 50, it doesn't matter. Beaker, not the most precise instrument, too big, and not enough lines in the middle of each major measurement for you to make good choices. Erlenmeyer flask, not something you measure stuff with, it's what you react stuff in. So that's why you choose A, and the next video we'll have 11 to 20 set up. Until then, good luck, I guess.